Okay, so what I would like to do today is move on to the air pollution concentration modeling unit. And what we will do in this unit is we'll initially start with looking at box models. And then from the box models, we will look at Gaussian dispersion. So in order to start, what I would like to do is to just review some of the concepts that we talked about when we looked at indoor air quality. So we'll do this with a couple polls. So I have launched the first poll. So if a system is at steady state, which of the following is true? Okay, you should now see the results. So if a system is at steady state, then yes, the change in mass with respect to time is equal to 0. Q in equals Q out may be true, but system can be at non-steady state, and that also can be true. So that's not necessarily true, or it's not true only for steady state systems. It's actually not true in all cases. We will always assume that Q in is equal to Q out. So as we'll see in this unit, we'll have situations where the system will not be at steady state, but Q in will equal Q out. And if Q in equals Q out, then the volume of the reactor is constant. But again, there are systems that are not at steady state, but the volume of the reactor is constant. The rate constant may or may not be 0. It can be at steady state, and you can have a situation where the chemical is reacting. And if it is at steady state, then yes, the concentration leaving the system is constant with time. So that hopefully helps in terms of trying to review some of these concepts. Let's look at this. So if the system is well mixed, what does that mean? Okay, so we have a situation here. If the system is well mixed, then the first answer, the change in mass with respect to time, that's the condition for steady state. May or may not be applicable. Second, we've got a constant volume, so we've taken volume out of the differential. That still equals 0. It's again a situation for steady state. May or may not be well mixed. The rate constant is equal to 0. That's a situation where we have a conservative contaminant. We may or may not be well mixed. If the system is well mixed, then the concentration leaving the system is equivalent to the concentration at any point in the system. So let's stop that and got one more. Okay, a chemical is said to be conservative if, a chemical is said to be conservative if it is non-reactive. Somebody else has a sense of humor like me. So a chemical that reacts according to first order kinetics is non-conservative, it's reactive. And most chemicals, I don't think any chemicals vote, but hey, if they do, well, I guess if it's conservative, you can decide. Okay. So hopefully just reviewing some of those concepts will help as we move through this material. So with concentration models, what we're trying to do is to predict the concentration of the pollutant resulting from a specified set of emissions for any location for any period of time with total confidence. Problem is, all models are wrong, some are useful, okay? No model that we have is 100% correct. However, some are more useful than others. What we want to do is to be able to do these predictions, recognizing the limitations of the models that we're using. So we'll look at two different types of models. We'll look at fixed box models, and that's what we'll start today. And we'll also look at Gaussian diffusion models. We will not look at receptor-oriented or source-oriented models. That's beyond what we have time to do in this course. So fixed box models. This is analogous to what we did with indoor air quality. These are simple to use. They're useful if there's many point sources or area sources, as we can aggregate those. They're based on the mass balance principles that we've used in the course, based on the concepts that we just reviewed. And we can use these for both conservative or reactive pollutants. And you'll see with Gaussian dispersion modeling there, we will only use the models for conservative pollutants. Now, what we have is we'll assume this situation here where we have a fixed box model. So we'll describe this, it could be a city. Problem we'll look at is described it as a peninsula, could be a valley. It's some land mass, and that land mass has width, length, and height. This height, we just finished determining the mixing height. This height here is our mixing height. Mixing height that we just learned how to calculate. We are going to assume that the wind is into the width of this land mass. So switch to the highlighters. So this here, area here, is the front face of this land mass. And air moves into that face, and it will move out of this face. So it's going to move in one side, and it will move out the other. And it moves in with a velocity of u. Typically, what we will use for the u is at 1/2 the mixing height. So similar to what we've done with those meteorology problems, we will use those same concepts here. Now, we will also assume that we have complete mixing in this volume here, so that the concentration at any point in the system is equal to the concentration out. So if we have complete mixing, that is correct. We will assume that this upper region here is completely separated from the lower region. So there is no transfer of pollutants out of that landmass, out the top. The only transfer that we have is out of the opposite face from where the landmass enters. We will also assume that that wind velocity is constant with elevation, it's constant with time, it's constant with location. So U is the same. We're going to use typically U at 1/2 the mixing height. And that is the velocity that we will use for that entire face. We will typically use the term B for the concentration entering the city. Back when we looked at ambient air quality, we used the term C sub A. And we will use the term emission rate, which we will assume is constant. This is in units of mass per time. It's Q. Q sub S is in mass per area per time. And we'll use the width and the length. So this area that we use, think of it as the bottom, the base of this rectangle, this rectangular prism, really. Okay. That base, that area is what we'll use for the area. Questions? So as I mentioned, no pollutant leaves except along that Y direction out of the opposite face. And the degradation can be modeled as a first order reaction. So we've got dC dt is equal to minus Kc, and K is in inverse time. So we use first order kinetics to model these reactions. Now, just as we did with indoor air quality, the mass rate of change is equal to the mass rate entering minus the mass rate leaving. So we can write that mathematically as the change in mass with respect to time. That's equal to change. Mass is equal to concentration times volume. The volume is the length times the width times the height. And in going from here to here, we've assumed volume is a constant. Okay, so if volume is a constant, I can pull volume out of the differential, and I now have the volume times dC dt. We then can write this using conventional terms. So we have a term for the mass entering from the source. We have, or I'll write this through the face. Okay. So we have the mass entering from outside of this rectangular prism, or outside of this landmass. We have the mass leaving through the opposite face. And then we have the mass reacting. And notice this is KCV. It's exactly the same term that we used with indoor air quality. The approach that we're using is identical to indoor air quality. There's some changes. Remember, in indoor air quality, we used air changes per hour. Here, we'll be using velocity. So we used a ventilation rate or an infiltration rate in indoor air quality. We're using velocity here. And if you remember, okay, we took air changes per hour times volume, we had volume per time. Here, if we take the velocity times the length times the height, so it's the area of that face, that is also equal to volume per time. And if we go back here, look, okay, this is the area of this face here. So it's the width times the height. And did I write length? Sorry, I'm going to fix that. It's the width times the height. Okay, so that's the area of that face. We can integrate that previous expression from, we integrate from time 0 to time t, and from C0 to C, we have this expression here. So we have a term here for the source within the landmass, that B is coming from the adjacent landmass from outside. We have a term, the exponential term, similar to what we had with indoor air quality. I've just written this as plus or minus. So it's minus if we have decay. It's plus if we have formation. So the chemical is actually forming in this landmass, it's plus. And then we have that term for the initial concentration. So if we have a steady state conservative pollutant, we can use this expression right here. So steady state conservative pollutant, so the K term drops out. The exponential term also drops out, as we showed with indoor air quality, and we're left with this expression here. If we have a non-steady state conservative pollutant, so K is equal to 0, the K term drops out. B is equal to 0, so if here is our rectangular prism, in this case, I'm going to draw it here with air entering into the screen and leaving out the back of the screen. So this is the height, this is the width, this is my length. And now here, the B is equal to 0. So the concentration entering is equal to 0. And we can use this expression here. All of these expressions are derived from that original larger expression that I gave you. What I am going to have you do now is I'm going to use Breakout Rooms. I've put the link to the Google Doc in the chat. I will also do it as an announcement when I set this up. And we'll do 7 breakout rooms. I am just going to put you in, actually, we'll do 6. Okay, so I will set up the breakout rooms. I've set this up with the breakout rooms where each of you will have the description. You actually have all of the equations. So you actually have the full text of the PowerPoints. What I want you to do is in your breakout rooms, I want you to, one, draw the best you can, diagram of the system, showing the flow of methane into and out of the valley. Once you've done that, then write the general mass balance equation describing the fate and transport of methane, state your assumptions, and then the last part is actually the part that I'm least concerned about, but at least if you determine the equation that you're going to use, or at least set up the equation to determine the steady state concentration in milligrams per cubic meter. So let me assign you into groups. And then once I've done that, I will post the link as a announcement. It's also in the chat. So if you want to grab that now, I realized I forgot to set the time. Okay, should be all back. And hopefully that was helpful. I saw that most of you, that you were all working through this. While you were working, I drew the diagram. So you should have something that looks like this. So what do we have? We have a situation where we've got a valley. We've described the valley, or provided the dimensions. Then we have a mixing height of 130 meters. We're told that the width is 4 kilometers. So the air is entering through this face right here. It leaves through the opposite face. You're told that the air entering has a concentration of 1.24 milligrams per cubic meter of methane, and that the flow rate is 2.4 meters per second. You are then told that there are 3 CAFOs, so combined animal feeding operations, each with an average of 1,500 cows. And you are told that the cows are emitting methane at a rate of 12.2 grams per hour for each cow. And you're also told that there is fracking in this valley. There are 1,420 wells, and each well is emitting methane at a rate of 2.5 grams per second. And you're given a first order rate constant for that system. So we have a situation where we have complete mixing within this land mass. We have no pollutant leaving other than through this back face right here. Okay. So it enters through the yellow face, leaves through the orange face that you see towards the back. Okay. Any questions so far? Okay, so the next thing we want to do is we want to describe the general mass balance equation. So we have the change in mass with respect to time is equal to the mass in, so that's through the face, plus the mass rate from the CAFOs, the mass rate from the wells, the mass rate leaving through that opposite face, and the mass rate reacted. Okay. And we can write this, if our volume is constant, we can pull volume from the differential. We have V dc dt is equal to the rate in is equal to our velocity times the concentration times the area of that face plus the rate from the CAFOs. So we have 3 CAFOs, 1,500 cows per CAFO, and 12.2 grams per hour from each of those cows. So this is the mass from our CAFO, plus the mass from the wells. We have 1420 wells times 2.5 grams per second, minus the mass out. So that is our the concentration times the velocity times the width times the height minus K, C, V, and V is volume, height times length. I'm going to stop there since we're 1 minute over. We'll pick this up on Monday, where we'll go through the rest of the assumptions and we'll go through the rest of the problem. And then I will do a second problem, and we'll do that also in breakout rooms. So happy to answer any questions that you may have, but we'll pick this up on Monday. Otherwise, have a wonderful weekend.